Well, I thought that was it for question 3, but it's not. We're stating the range of CT, so stating the range of our functions for part C. So we already know we're going from 18 to 26, so that's our range. We just put it in square brackets. As for D, calculate C8 and state the time of day when this first temperature occurs. Okay, so we're saying C of 8 is at 24 degrees. Now, if we look at our graph, that's at 26, 24 degrees. So I'm going to say, let's go graph at 24. And here it is. Menu. Go to analyze. I'm going to check the intersection between these two. Lower bound, upper bound. Okay, it happens. Okay, so calculate C8 and state the time of day when the temperature first occurs. So it happens at 8 hours. 8 hours, we don't just write 8 o'clock, we write 11 a.m. because it measures time after 3 a.m. Another way they could have asked this question, and I would have said, where else does it happen? I would have said analyze graph intersection here and here. I would have said analyze C16. So not that. I would have said calculate C16. So I would have gone here. So C16, 24, and then you think, oh, it happens then, but no, then you have to actually go here. Oh, it also happens here. That's the way I would have done it. That they could ask you that. I don't know. I don't remember, but I just think that's something they might try to do. Okay, so we're looking at part D now. So we've done D. E. Determine the values of T and hence the other times of the day that the temperature in the computer lab is C8 between noon today and midnight. Okay, so when else is it at C8? Let's have a look. So it's the same temperature here at 16. Now it's between 12 noon and midnight. So this is 3 a.m. This is 3 p.m. This is 4 hours after 3 p.m. So it's at 7 p.m. 2 marks. Yeah, I'd be writing some of that information there. Over one day, find the fraction of time in the computer lab is equal to or less than 20 degrees. Okay, so we are finding where it is equal to 20. So we're looking for here and here. Alright, so what we're going to do is we're going to find when it's below this. So we're going back to here. We're solving C of x equaling 20 for x. X equals 4 or x equals 20. Now, I'd just like to show you something. I just want to give you this. If I did not define a domain, and I do this, it gives me this business with ends. They're just telling us multiples and things like that. We don't want that. That's no good. That's why we always define our domain. Define your domain, and then that lets you solve stuff. Alright, so it's happening at x equals 4 and x equals 20. Alright, so based on, let's go back to the question. Over one day, find the fraction of time that the temperature in the computer lab is less than or equal to 20 degrees. Okay, so it is less than or equal to 20 degrees at 4 hours and then at 20 hours. So let's see. So perhaps from 0 to 4 hours and then from 20 to 24 hours. So from 0 to 4 is 4 hours. So let's write this down. So we've got 0 to 4 is 4 hours. Then from 20 to 24 is also 4 hours. Hence, it is at most 20 degrees for 8 hours. Okay, syntax. Okay, done. So for 8 hours, let's go. No, I've got to leave. Control A. Okay, so it's happening for 8 hours. So we do 8 over 24. Multiply that by 100. So we end up with by that 33%. Find the fraction. The fraction, so it just ends up being a third. Okay, now the temperature. Let's see. The maximum temperature in the computer lab on any day is reduced to 25 degrees with no change to the minimum temperature. The temperature now given in the computer letter now is R degrees and time T hours 3 a.m. So everything else is the same, but we've just changed around a couple of things. So the maximum temperature is different, but the minimum temperature is not. So let's have a look at our thing. So this has been brought down now to 25, but the bottom is still 18. So if the bottom's still 18, let's have a look what we've got. Oh, no, no, no. What is going on? Why is that happening? Oh, these are my other programs. Oh. Okay, here we go again. So, let's see. C of x is this. So, 22 minus 4. And then it's going to be 22 plus 4 for the maximum. So that's what we end up with there. So something here changed. Now, we could say 22 rather than 22. Can I get 21 minus 4? So let's go R of x. We redefine this thing. We're using the same thing. We're calling it R, exactly like they do. R of x equals 22, let's change it to 21, so that brings it up to 25 then. So now I'm going to graph that, and I'm going to say menu, I'm going to go here, I'm going to tab, I'm going to say R of x. And as we see there, it's gone down, but this is not right, we've had that drop. Okay, so based on that, let's go back to this. That tells us we've got to change these kind of the same way. So if we're at 21, we want to pick up 25. I'm just trying to work my way through this. What I'd be saying, and I'd like to write this stuff down, is there's a little graph. We know that from our midpoint of 22, and let's graph 22 so we can see what's going on. That's our midpoint for the first one. We go up 4, we go down 4. So from there, that's what our amplitude comes, but we want the same minimum temperature. So we want to go from here to, we're going from a minimum temperature of 18 up to a max temperature of 25. That tells us that it's 7. So we've got an amplitude of 3.5. So let's see what we can do if we set our amplitude to 3.5 rather than 4. So we're going to change this to 22. And we're going to set this to 3.5. And we're going to go back here. We're going to have a look at this. So our new graph is now, our bottom temperature is still not right. Still not quite there. So as a result of that, I'd be saying we need to control tab. Do we need to change this to 21? No, that won't help. Where is it? It's 21.5. 0.5. So I've done this. I think it's some trial and error. R of 12. Yeah, there we go. So what I've done there, I've made it so that we still end up with a minimum of 18. So 21.5 minus 3.5, we get 18. 21.5 plus 3.5, we end up with 25. So that's what I was trying to find there. So I found it went to 7. It had a fluctuation of 7, which is twice 3.5. And then from there was a case of then adding and subtracting to 20 something to get 18 and 25 as well. Okay, so that ends up, okay, so we've got that. That's the values of A and B determined. Okay, that's it for that question. Just the probability one. Yeah, no, I'm not going to do that one right now. Let's have a look at this. So question 5, I said to do A and B. Apple has gone into the ice cream business. Yay. They have developed a new product called the ice cream. A revolutionary new ice cream cone, but instead of being cone-shaped, the wafer biscuit is shaped into an open-top cylinder. That's interesting, hence we'll know it as the ice cream cylinder rather than the ice cream cone. It is designed to fill 220 cubic centimeters of ice cream without overflowing. Some relevant formulas include, okay, here we go, here we've got some formulas. Write down H in terms of R. So what are we using then? So we've got H in terms of R. if we're doing that, we're writing h in terms of r, and I'd be using this because it's information that I've got. So I'm saying 220. So this is where transposer formula with CAS. I've done it before, but we'll go through this anyway. So I'm running this new calculator. So I'm saying V of R, I think. Here's where you get called. So I'm saying define V of R. Oh no, we don't want to do that. Let's close this and start a new one. Alright. Define V of R equals pi r squared, pi times r squared times h. Alright, now if V of r equals 220, so we're saying, hang on, VR, no, write h in terms of r. So we're saying 220 equals pi times r squared times h. So we want to write h in terms of r. So we're saying h then equals we're just saying 220 over pi r squared. So we say h, so we're going to put that back up, pi r h, okay. So I can say solve this for h. Oops. That's what we end up with there. So that's where we go. That's h in terms of r. I don't know if we want to use this. We may want to use this thing. So we could try a of r, the area, but we don't have any information. So we'll just leave that as this. Show the total surface area is given by this r. Okay, so we've got our h. So if that's what h equals, then we know we've got our total surface area. So we're writing this in terms of r. So say a, define a of r equals, now we're going to write this thing in, pi times r squared plus, no, we're not doing that, pi rh, pi times r times this. That's our value for h. Done. So now say a of r, 220 over r, that's not right. Aha, that's just the curved surface area, the total surface area of the cone. Oh, scream silly, this is, oh. So yeah, the curve, that's the curved surface, 220 over r. We've got to double it, I've got to double it. So we'll put a 2 here. We're going to a. I'm getting very tired and I'm making mistakes because of it, running out of time too. So that's what we've got there. So that's a curved surface. We know we've got pi r squared. That's because that's the bottom of the cone. The bottom of the cylinder, so that's what we'd say. And now we've got our calculus. So, well, what do you know? I've put it in. Surface area and there's a surface area of the minimized, and that's it. Got it in 15 minutes. So that's another question done, and that'll be it.